Good afternoon to Professor Wataru Takeuchi, konnichiwa, and also good afternoon to Professor Atsushi Higuchi, konnichiwa. Good afternoon to everyone, ladies and gentlemen. Welcome to the pre-conference episode 2021 third tutorial series. Episode 2021 holds pre-conference activities with online tutorial series on synthetic aperture radar or SAR, collaborate with the IEEE GRS Technical Committee of Instrumentation and Future Technologies or IFT, IEEE Indonesian Section, and Indonesia Remote Sensing Society atau Masyarakat Ahli Penginderaan Jauh Indonesia. And in order to boost the knowledge on SAR technology, including the SAR hardware and image signal processing for young scientists and students. And today, ladies and gentlemen, we have three amazing speakers and also with the three interesting topic that we have been waiting for. The first topic is microsatellites and the application that will be brought by Bapak Dr. Wahyudi Hasbi. And then the second topic is the infrastructure health monitoring with SAR technologies that will be brought by Professor Wataru Takeuchi. And the third topic is the third generation of geostationary satellites utilization or geosatellite utilization that will be brought by Professor Atsushi Higuchi. And obviously, this tutorial can be accessed in Zoom application. So therefore, to all the audiences here, ladies and gentlemen, are suggested to download the virtual background. You can click on link that's just sent by the host at the room chat. So maybe the host or the co-host, can send the link for the download for the virtual background. And not forget that this tutorial is being streamed also live on the IEEE Indonesian YouTube channel. And I want to remind you that our host and our co-host will inform you links at the chat room that those are about the question form. So to all of you, ladies and gentlemen, all of the audiences here who want to give a questions to our speakers today, you can click on the link question form. So we as a committee can read and choose your question to the speaker at the time of Q&A section. And also there is an e-certificate link. So I hope to all of you, ladies and gentlemen, could pay attention from the beginning into the end of this memorable tutorial series. These tutorial series are supported by IEEE Indonesian Section, GRSS, Institut Teknologi Bandung, Institut Teknologi 10 November, Masyarakat Ahli Penginderaan Jauh Indonesia, Chiba University, LAPAN, and BPPT, and also hosted by the IEEE TS student branch. And then allow me to introduce myself. My name is Aloysius Krishna Wikantioso as the master ceremony for the third tutorial series for the episode 2021. And I'm the college student from the 10 November Institute of Technology, ITS, at the Electrical Engineering Department. Okay, now for the first agenda that we are heading on is the opening speech by Professor Josafat Tutuko Sri Sumantio. But unfortunately, because some kind of unavoidable jam, so Professor Josafat for now could not attend this tutorial. But that's okay, because this opening speech will be represented by Bapak Dr. Wahyudi Hasbi from National Institute of Aeronautics and Space Indonesia, or LAPAN, and also as the chairman of the IEEE Indonesian section. It is such an honor to get you here, Bapak Wahyudi Hasbi. So please to Bapak Dr. Wahyudi Hasbi, the time is yours to give the opening speech.
Thank you, Mas Krishna. I will start my screen first. Okay, I believe that you can read my screen, right? So, okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. First of all, I would like to thank Professor Takeuchi and also Professor Higuchi that can attend this this tutorial in this afternoon. Even though I know that you have a busy schedule, but again, thank you very much for your kindness to and spend your time to give us your insight for today's tutorial. So before we start our tutorial, actually, I would like to again remind all of you, all the participants and distinguished guests, that this tutorial series is actually developed in order to have some kind of pre-conference of APSAR, or Asia Pacific Conference on Synthetic Aperture Radar 2021, that we will be held in Bali Island from 1 to 5th November 2021. So I hope that all of you can join this conference, and you can submit your papers. And of course, at the beginning, you just need to submit your abstract and then continue with the papers and so on. So we already start this tutorial, and now we came to the tutorial series 3. So previously we have the first tutorial on 11 March 2021. During that time, this tutorial given by Professor Josaphat, and also Professor Yamaguchi and Professor Hongbo. And also the second tutorial is given by Professor Aris Marfai from Badan Informasi Geospatial Indonesia, or remote sensing, with the title of Remote Sensing Technology for Mapping. And also from Professor Hirose from University of Tokyo, Japan, and also from Professor Feng Zhu. So, and today tutorial will be given by myself, and also from Professor Takeuchi, and the last tutorial will be given by Professor Higuchi. So we know that we will continue this tutorial to until 5th tutorial, and then you can see the schedule here. We have after this tutorial, we will have the 4th tutorial on 22nd April. And this will be the distinguished speaker will be Dr. Agustin from BPPT Indonesia, and also Dr. Meta from Netherlands, and Dr. Yunis from Germany. And also the last tutorial on 25th May 2021 will be given by Professor Bhattacharya from IIT Bombay, India, and also Professor Simada and also Professor Gao. So we believe that this tutorial will give you a lot of knowledge and insight, so that we will get to know many details on this SAR technology, and then this will increase our knowledge, of course. So I would like to remind you that we welcome all the papers for our conference. We will be held on 1st to 5th November in Bali Island. So this Asia Pacific Conference is the first time will be hosted in Bali, and this will be very important forum for all of us to have a lot of networking, and of course we get the latest technology development in synthetic aperture radar. So I believe this will be very important conference. And then if you go to our website, you can see the call for paper for this Asia Pacific Conference, and you will see here the important dates. So the important dates at first is the abstract submissions deadline. That will be very soon close on 30th April. So I strongly recommend you to submit your abstract soon. And then later on, once your abstract is accepted by us, then you can go ahead with the paper submissions, which will be the deadline on 31st May. And then we will notify you about the paper acceptance on 1st of August. And of course, the deadline for the final paper submission will be the 1st September 2021. So you can see here a lot of technical program and scope. And there are so many scope here related to the remote sensing technology as well. For example, SAR platform, interferometric and polarimetric SAR, multiband and multi-beam SAR, planetary SAR, SAR and radar system, SAR image processing, also about SAR application, and also moving target and detection. So a lot of scope here can be included. So we welcome all your contribution to this conference. So again, you just remind you that the 30th April will be the abstract submission deadline. So please submit your abstracts very soon, and then you can continue with other paper submission deadline and so on. So with that, I conclude my welcome remarks on behalf of Professor Josaphat as the General Chair of APSAR 2021. I give it back to you, MC. Thank you.
Okay, thank you so much to Bapak Dr. Wahyudi Hasbi for the opening speech. Yeah, I would like to rememorize to you, ladies and gentlemen, about what the Bapak Dr. Wahyudi Hasbi has just said about the important date of the APSAR 2021 series of event, that the deadline for the abstract submission at the 13th April 2021. Once again, the deadline for the abstract submission at the 13th April 2021. So to all of you, ladies and gentlemen, who have interested for joining at the APSAR competition, and there's a lot of time for you to prepare your abstract to submit into the APSAR 2021. So let's give your best idea into it. And then the second is the deadline for the paper submission at the 31st May 2021. Once again, the deadline for the paper submission at the 31st May 2021. And maybe, ladies and gentlemen, for the further information, you can also check into the website of the APSAR 2021 at the www.apsar2021.org. Okay, so without any further anymore, let's get into the next agenda that we have been waiting for. And maybe I think this is my time to stop being screen at your Zoom, ladies and gentlemen. And so please welcome to our moderator. Okay.
Well, thank you very much for Mr. Krishna as I'm master of ceremony today. Here, good afternoon, everyone. And I would like to say good afternoon to Mr. Wahyudi Hasbi as the as the chairman of the Indonesia section joint chapter of IEEE. And here, first of all, I would like to introduce myself. My name is Taifatul Uma, and here I'm a master student from Department Geomatics Engineering Department Institute Teknologi 10 November Surabaya. Okay, here we have for the first speaker, he is Mr. Wahyudi Hasbi, and he will be delivered under the topic is microsatellites and the application. And good afternoon, Mr. Wahyudi Hasbi.
Good afternoon, Mbak Ulma.
How are you today?
I'm fine, thank you. How are you?
Okay. I would like to remind you your time for the presentation is about 1 hour and followed by question and answer section. Okay, time is yours, Mr. Hasbi.
Thank you, Miss Alma. So let me start my screen again now with different topics. All right, so I believe you can see my screen now again.
Yes.
Okay, so first of all, I would like to congratulate IEEE student branch Institute Technology of Surabaya for hosting this great and also organizing this great tutorial. And of course, my deep thanks also to all the participants who can join this tutorial series number 3. So, okay, my topic today will be microsatellite and applications. And actually, just to introduce myself, I came from Satellite Technology Center from National Institute of Aeronautics and Space. And then, okay, so, and currently I also become a vice chairman for the APSAR 2021 and also chair of IEEE Indonesia section. Okay, so the topic about microsatellite and application, and of course before that I would like to inform you, and maybe some of you already knows that there are several satellite class, and then we know that large satellite is typically named as the large satellite with more than 1,000 kilograms. So basically, it's divided into several weight class, and then medium satellite like 500 to 1 ton, and mini satellite, let's say between 100 to 500 kilogram, and also microsatellite between 10 to 100, and up to femtosatellite. You can see here there is very small satellite called femtosatellite. It's about 1 gram, right? So it's very small. And then you can see the comparison between the large satellite and very small satellite like CubeSat here. So this is 1U CubeSat. So they call it 1U because the size is 10 by 10 by 10. So the total volume is about 10 centimeter cubic. And then this will be very small. And then in the right side is a microsatellite, which have weight about 100 to 120 kilograms, let's say. Okay. And if we are talking about small satellite application, there are many applications that can be done by having a small satellite. At first is like Earth and space observation, and then you can have optical and SAR or synthetic aperture radar as a payload of this small satellite. I can show you later how it can be done. And also for IoT or Internet of Things and communications, and you can use the small satellite as well for asset tracking or M2M, and also science and environment, security, defense, and national space program, and any other small satellite application. So we see now in the world, there are a lot of satellite technology and new trend. You can see here, there are many increasing of non-GSO. GSO means a geosynchronous orbit satellite, specifically for communication satellite. So usually there are many geosynchronized orbit satellite, but nowadays we see a lot of increasing in non-GSO, which means the satellite height or altitude is below than 36,000 kilometers. And also there is a demand of increasing of high throughput satellite for broadband application. And we also can see there are many or increasing of commercial small satellite for remote sensing satellite. And we also see that satellite business is not only for government agency, but also for a business entity. You can see here a lot of money already invested in the space technology, like OneWeb, for example. SpaceX, we know already invest a lot of money on that. Planets, constellation, Aspire, and so on. So now business entities also go into this direction. And this is just some example of new communication in infrastructure starting from UAV to geosatellite, right? And here on the left, right, on the right below, you can see here some kind of lights. People typically say this is a train satellite because this is the SpaceX satellite, and they are moving just like a train in the orbit. Yeah, and this is a small satellite for remote sensing. They call it as a DOF, and they have more than 100 plus numbers in orbit now. And another statistic that you can see here, like a trend on small satellite development. You can see here the launch of many small satellite, and you can see here typical application is Earth observation and also the communications. Yeah, and then here you can see here as well the CubeSat development as well. So it's increasing very fast. And another market trend on the machine-to-machine communication, you can see here the growth in the IoT by application like for agriculture, constructions, mining, oil and gas, maritime, transport, and including consumer IoT. And we can see here the demand and increasing as well for IoT for cargo and also transportation. Yeah, and on the right side you can see here the maritime small sat IoT also increasing. So the IoT small sat is also one of the demanding application. Another statistic about launch history of small satellite. There are a lot of small satellite in numbers increasing to be launched, and I believe that within 5 years we will have more than doubles that we have now. And the question is why we want to have or we want to develop the micro or small satellite. The first thing is because by having the small satellite or micro satellite, you can just use the current advanced technology. So you have to understand that the satellite technology is typically a conservative technology, which means once you find something, typically you don't want to change it. But with the small satellite class type, you can try to use the current advanced technology. And of course, this will be it will be benefit for you. And another thing is we have an opportunity for international cooperations. You can see that a lot of students can have international cooperation in developing the microsatellite, nanosatellite, or CubeSat satellite. And you can have access to knowledge, skill, and experience as well. And then with the micro or small satellite, you can carry experimental and demonstration mission payload so that you can ease of the satellite development. You can simplify the production and test facility. You know, if you want to make a big satellite, of course, you need a very big facility. But if you like to make a small satellite, then you don't need such a large test facility. And of course, because the satellite is so small, so you have only you just need to have shorter development time. And because all of this, of course, this will reduce the cost, right? And one more important thing is because by having this small satellite, you can launch the satellite as auxiliary payload on launch vehicle. So you can put your small satellite in the same launcher as other big satellite. And of course, this small satellite is not only used by government, but it can be developed by private company, universities for experimental application and technology demonstration. Yeah. Okay. And then another question is why it is small? The answer is here. You can see. Yeah. So first is because the solar cell development efficiency is growing very, very nicely. You can see many years ago, the solar efficiency is very low, like 16%. Now it's increasing double, like 33%. So with the small size, you can get the higher efficiency so that you don't need such a big solar cells, of course. And then the battery as well. The battery efficiency and capacity also is growing. You can see the increasing of the battery capacity compared to the size. Yeah, and another things like the here is some the image of small thruster. So in many years ago, you need have a big thruster, but now you can develop small thruster to put into your nanosat or microsatellite, including for example here some reaction wheel. You need a reaction wheel to control the attitude of your small satellite, right? And also gyros and other other structure. So here in the left side, you can see the CubeSat size is a 10 by 10 by 10. So you can put a lot of experiments on that, and you can launch it. And this is a typical CubeSat that developed by many universities. So they put the a dipole antenna system which can be unfold, yeah, like this one, and then with the solar panel, and you can put some a power system, UHF radio, and flight computer, of course. And in this occasion, I would like to share with you why we are in Indonesia, or let's say Lapan, also develop this microsatellite. The reason why is because we have many experience already in the space activities. So starting in let's say 1971, we already used many image from remote sensing satellite, and then moving forward, we think that we should start to develop the satellite technology, and not only the satellite technology but also UAV and aircraft for that, right? And then this is our roadmap. Maybe some of you already know that. So we start to develop our microsatellite in 2007. We learn about it, and then afterwards we launch it. We launched the satellite, and then we developed the second satellite in Indonesia, and we are moving forward now to develop our fourth satellite, and later on will be the fifth satellite. And then this is one of our first satellite. This is microsatellite. The weight is about 50 kilograms, and you can see here very nicely the video coming from this small microsatellite. So it's just like you are in helicopter, and then you are moving around, like you want to see some very interesting one, like maybe you want to see the top of the mountain here in Napoli, Italia, and then you can move around and see any object on Earth that will be interesting for you. Yeah. So this is also one of the nice target that that you can see. And then this is another sample of video. You can see that how we are getting the video image of Merapi Mountain in Java. And then from this video, we process the video, become an image. So we make a technique of framing and stitching process, so that we can have large area of imaging like here. And then we make image enhancement and also georeference process for that. And then we will have this kind of image, this Merapi area, and then by having this this image, we can make land use information out of it, right? Okay, and then this is another image of our first satellite. We can get many image of city in the world because you have a satellite, so you can take image in any country in the world, right? So there is no regulation can skip you to take an image in any other country or area in the world. Like here, we take a image of Singapore and Amsterdam, and of course our Bromo Mountain, Mahameru Mountain, and also city in Semarang, and also Surabaya before the bridge is finished. And we developed our second satellite. We call it Lapan-A2 together with amateur radio. We developed this satellite also as a microsatellite because the weight is about 76 kilograms, and we put a lot of things inside. You can see we are using 4 solar panel, a lithium battery, and 2 TTNC, and also the S-band for data downlink. And we are using 32-bit processor to handle the data. and some attitude control system like a wheel, gyros, and star sensor and sun sensor, right? And the payload is the camera and also some video cameras and AIS for ship identification and also for amateur radio, voice repeater, and automatic package reporting system. And this is some of the application that we can see by having this 882 satellite. We can take an image of the new toll road in central Java, for example, and then we can take a look of city in Semarang, also in Java, Monas area, and some area in Singapore and Malaysia, for example. And because we have an AI system, then we can also take a lot of ships monitoring around the equatorial belt, because the satellite is having equatorial orbit here. And also the satellite used by the amateur radio for voice repeater and also send data through automatic package reporting system. And this is the typical application that we are using for our 882 and 883. We use it for Earth observation to get image of our country, of course, and especially for disaster. We need to know the situation during a disaster. So we use the satellite to capture all the details. Like here, for example, in 2021, during the Krakatawa eruption, we can get the image out of it. And yeah, we know in liquefaction in 2018 as well, and some eruption of Agung Mountain in 2019. And also we take some image of forest fire, a big forest fire in Vietnam. And the satellite also have another payload to get the Earth magnetic field. So we measure the Earth magnetic data around the globe, and we have the data out of it. And another things that we are using is we detect all the ships around the world by having the 883 satellite, because it has a polar orbit so that we can receive all the data from all the world. And also here we can get the equatorial AIS information or ship information around the equatorial belt. And this is the 8 emitter communication during disaster. So this is some details about AIS, or we are using the satellite for maritime surveillance. You can see here the red color means the data coming from 882 satellite, because the orbit is only in equatorial line here. And the yellow is the ship's information we get from our 883 satellite. So this is when we combine those two data, we can get the big picture of the maritime situation in the whole globe. And this is some of example how can we use this AIS information to see the suspicious ships moving around our island, and then seems that they want to make illegal fishing around our country. And this is another example how can we track ships that hit our coral reef in Papua regions, and we know how they are hit our coral reef in this area, including time and when it is really happens and how long they are staying there. And this is another example of the application. So we use our 883 satellite to get an image of Jakarta, for example, here, and another city in Medan, in Denpasar, Bali, in Singapore. From this image, you can see, because this is false color between red, green, and near infrared. So you can see here, if there is no red here, meaning the vegetation is very low. And yeah, Jakarta is a big city, so that we know that the vegetation is low, and we can see by the color here compared to Medan, for example, or Bali here, right? And then This is another image from other city in other country, like in Spain. We can get a bit high resolution image in with 3.5 meter resolutions, and in Portugal we can also take some image out of it. And then this is one of example how we can compare the big satellite data like Landsat 8 and our small 883 satellite image. And by having the comparison is quite nice. So the overall accuracy about 93 and 95% for five parameters. So it's quite okay for us. So I can inform you that, of course, when you can develop the small satellite for this application. And this is another image like Bangkok, Ho Chi Minh, Phnom Penh, Kuala Lumpur, and other country. And this is another sample of image like White City is one of my most favorite image. Is this city is very nice colors and so on. And Mecca in Saudi Arabia, and Dubai here, Auckland, Cairo, including Las Vegas, right? So we can get all the image from our small satellite. So another thing that we are doing is because we have very compact satellite, so we can put any other payload. Like one of our example here is we are overlay the thermal imaging and also the multispectral. And by having that one, we can try to find some important data out of it. And then as we know that Indonesia is very we have a country with a lot of potential of natural disaster. So there are increasing number of natural disaster in Indonesia, and of course we have to make a technology that we can use that so that we can have some mitigation, or we know what happens in during a disaster. And then this is some of example how we used our satellite to capture an image during a disaster. For example, here during the tsunami in Palu in 2018, we can see the liquefaction happens in this area. And then during the Mount Agung eruption as well in Bali, you can take the image of the mountain. And also during earthquake happens in Lombok area, we know that and on the top of Mount Rinjani there are thousands of people trapped because of there are many subsidence happens there. And by having the satellite image, we know that this area is having some subsidence happens there. And then another thing is, of course, we Indonesia is also located in the Ring of Fire. We have a lot of earthquakes, and this will be very dangerous for us. And specifically, we know that most of the people living in Java Island. And then, yeah, you can see here the map. We are living in the Ring of Fire. And another sample how we use the satellite during a disaster. So we can see here, for example, before the Krakatoa mountain erupt in 2018, we can see all these three islands all shows that the color is red, meaning the vegetation is there. And how about this one, right? We can see that the color is changing after the eruption, and we can see here the ash coming out from the mountain. And we believe that the vegetation here is covered by the ash from the eruption of the mountain. So here as well, another picture, and this one as well, right? So, and then we can see here lot of materials coming out from the Krakatoa mountain as well. And this is another details of liquefactions in Petobo area in Palu. You can see here, and also this is landslide in Rinjani Mountain. There are many tourists trapped on the top of this mountain as well. And then there is some close image of Mount Agung in Bali. And this is another a good example of how our small satellite can respond to the forest fires. A big forest fire happens in Vietnam, and we took the image on 6th July in 2019, and we can see here there are 3 locations with very big forest fire happens in this area. You can see here when they use this data and they make the map out of it. And also we also take an image of Kagoshima, Japan during the big flooding happens there, and if we zoom in there, then we can see there is a lot of colors difference before and after the flooding happens there. And another payload that we are using in our satellite is, as I mentioned before, that we are using the satellite to measure the Earth magnetic field for our globe, and you can see here the North Pole and South Pole, and this is the South anomaly happens in Latin America, right? And then another payload that we are putting in our satellite is we are putting the amateur radio voice repeater on there, so that during a disaster happen, you just need to use a handy talkie, which is very cheap, less than $20 you can buy in any market. And then by having this handy talkie, you can talk to other people which separate about 2,000 kilometers by having our repeater in our satellite like this one. And then this is a typical schedule during if there is a disaster really happens and become a national problems. Of course, we will activate our satellite only to become a repeater for all the disaster communication. And this another sample, you can see that people use the handy talkie like here as well. Yeah. And then one more I want to show you this is very recent problem. So this gentleman only use a handy talkie, like I mentioned to you during the a big flooding happens in Sulawesi area. So this gentleman making voice communication by using his handy talkie and repeat by our satellite and can be heard by any other amateur radio within the range of 2,000 to 3,000 kilometers. Okay, and then because of that, we know that because we are prone for disaster. Of course, we need to teach our people. So we teach our people how to use the very cheap equipment to talk during a disaster, and we teach them how to use the satellite as well. And then this is another sample on how the amateur radio making what's so-called amateur radio IoT and messaging system. So they can say hello, send a message, SMS like SMS to their friends through our satellite. So it's very simple communication, only using handy talkie and APRS protocol. And then this is another sample how they can communicate. You can imagine from Java to Australia by using only handy talkie. Of course, not only using handy talkie, because in the middle there will be be our the message people. And then know they happen, then we get the satellite and also will be used for 5G, and the typical satellite will be used is of course for massive machine type communications, including the IoT systems and M2M. And you can see here that the satellite has to cover up almost 3,000 devices in a single cell. And this can be done only by using a satellite. And this is a bit related to our topic about SAR. Even for synthetic aperture radar, the satellite is also getting smaller. And you can see here some synthetic aperture radar coming from small or microsatellite. From here is the Capella space. They can take an image of Dubai area. And ICE is about 80 kilograms something class satellite. And in the left side, I would like to show you here the first image of Professor Josaphat CPSAR. So they take an image in Sulawesi area by using a plane, of course, for testing it. And later on, once everything is in a good way, we can also have a small satellite for synthetic aperture radar in circular polarization, so we believe it can be done very soon. And this is what I would like to mention to you again, that typically the SAR satellite is very big. Like here, it's about 2 tons. Why we need such a very big satellite? Of course, because we need a lot of generating power, right? So the challenge is, of course, generating power, imaging efficiency, and then frequency and resolution of your image. And then nowadays, the SAR satellite is also getting smaller. You can see here the NovaSAR from UK. They are growing down now to 400 kilograms compared to 2.2 tons here. And ICE is now getting smaller, like 85 kilograms. And also another typical SAR is called as Capella XR, is about 48 kilograms. Of course, this will be a big question, how they can generate really a good power to get the very nice image, right? So this is a challenge or engineering challenge. How can we make a small satellite for synthetic aperture radar? And we will answer it soon together, right? Okay, so this is maybe almost the last of my slide. So in Indonesia, I would like to share with all of you that we have all the facility right now to develop the small satellite, let's say up to 300 kilogram class. So we have a clean room here, 100,000 kilogram clean room class. And we also have several facility like thermal vacuum chamber to test the space environment for all the subsystem in the satellite, and also climatic test chamber and vibration test here. Of course, we need this vibration test so that the satellite that we are develop should be compatible with the launcher, right? And this is another facility like integrating spare. This laboratory is very useful when you want to test your camera, lenses, and CCD and CMOS sensor and so on. And then we also have this one is the biggest anechoic chamber for radio frequency and electromagnetic compatibility in Indonesia. This very large is a full range of anechoic chamber. And then I welcome all of you if you would like to make any tests in our facility. Another things I would like to show you is, of course, we have the full motion antenna that can transmit and receive in S-band channel. and downlink in X-band channel. Yeah, and then we have our satellite mission control center to control all our satellite that has been launched already. And then, of course, besides you need to have your facility, you also need your ground segment, right? Because once you launch your satellite, you need to control your satellite, and you need the ground station for that. And nowadays, we have several ground stations in Indonesia, like in Bayak Island, in Papua, in Parepare, in Bogor, in Pontianak, and Bukit Tinggi, and you can see here all the ground station. And not only that, we also develop a ground station in the North Pole. This is a station that we developed in North Pole for controlling our polar orbit satellite system. So we put it there in the very far away from our country here, right? So with that, I hope that you can have some important information or knowledge from this talk. So once again, I would like to thanks to you for your attention, and I hope to see you in our EPISAR conference in November. So thank you again. I give it back to you, Mbak. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you so much, Mr. Hasbi, for your great presentation and this topic so interesting for us. Okay, I think we will go to about the question and answer section, because there's so many question and answer for Mr. Wahyudi Hasbi for your topic before that. You have done. Okay, before we go to question and answer, I would like to remind for all the participants, for those of you who have the question, you can fill your question or ask your question into the link http:// bit.ly/Q&A Tutorial-3 Aperture 2021, or you can see in the chat Zoom. Okay, Mr. Hasbi, I think we will go to the first question. I would like to share the question. The question from Lampung University, and his question is: Indonesia has small satellites weather. Usefulness of satellites different depending on their size. Maybe the question is Indonesia has small to large satellites, whether the usefulness of satellites different depending on their size. Maybe about the resolution for the satellites weather.
Okay, so I need to answer it now?
Yes, of course.
Yeah, so you're right. So size of the satellite also will be depending on the mission, right? Mm-hmm. So if you have many mission or very specific mission, and then you can use a large satellite. But of course, as I mentioned to you, if you want to do something, of course, you need to really care about what you would like to do, right? So at first, you need to define your mission, what mission and what you would like to achieve with your system. So sometimes you don't need a large satellite to fulfill your mission. Maybe you just need a small size of the satellite. And moreover, I also would like to inform you that the cost of the launch is very expensive. The cost is about $20,000 to $40,000 per kilogram. Mm-hmm. So you can imagine that if it is so expensive, so you really need to carefully define your missions. and then and efficiently, you of course you need to make your satellites very efficient as well, and with a lot of system engineering aspect on that, so that you can have very low cost satellite, but with the full benefit, and your satellite can achieve your final mission. Maybe that's my direct answer. Thank you.
Okay, thank you, Mr. Hasbi. So the point is we have to define what mission for the satellite it will be, right? Okay. For the next question, come from Muhammad Farel Shuhada from Universitas Lampung. He has a question. Can we use 8A2 or 8A3 satellite for another function, except mitigation of natural disaster and communication during natural disaster nowadays?
Yes, good question. So actually, this satellite is not only only needed for mitigation during natural disaster. It's also used for regular mission. So our regular mission is to image the whole Indonesia, of course, and then to survey or to monitor our oceans or our maritime domain. And another mission is, of course, by having the satellite, the satellite also will be used to teach our people about the satellite technology. So this is the regular mission that we use when there is no natural disaster happens, of course.
Okay, right. Thank you. And then we go to the next question. Come from Bram. His question is, currently, how big is the contribution of the provided Lapan space capability to the government policy? And does it have a direct influence as the decision support system?
Okay, this is also a very good question. So yes, you are right. So once you make a satellite, which is very expensive, you want to have your satellite which can help you to make a decision, right? So for example, during a disaster or during maritime surveillance, you need a lot of data, and and I would like to also mention to you that there is no one system can serve or can support all of your needs. So if you make any satellite, let's say, and then it has functionality, then it will be very useful for others, of course. And the typical in Indonesia, for example, we use our data and we give this data to support our government policy. For example, for oil spill cases in our oceans, we also take an image of this oil spill happens in our maritime, and we give this data to our policymaker. And also for example, AIS information for the ships, we have a lot of data, and we also give this data to our maritime stakeholder as well. So yeah, you need to make your satellite useful for your country.
Mm-hmm. So does it have a direct influence as the decision support system, Mr. Wahyudi Hasbi?
Yes, for example, as I mentioned you, for oil spill, for example, so we have a cooperation not only between Lapan but also with any other agency, like for example with maritime ministry, and also stakeholders like law enforcement for maritime. So once we support this data, and then of course they can use this data to find who is the or the suspect who make this oil spill in our ocean.
Okay. Okay, thank you, Mr. Hasbi. Then we go to the next question. This is from Animals, and he just curious. Lapan has satellite A2 and A3. So is there Lapan have sonar too?
Oh, okay. I don't know what they mean about sonar. Like you want to make a radar something. If what it means, then no. We only take a image by using an optical systems, and also we are receive the AI signal from all the ships, and we are also have the system inside of our satellite to receive the signal from the magnetometer for magnet field for our globe, and also the communication by using the handy talkie, as I mentioned before.
Okay. Okay. So that's the answer. And then Mr. Hasbi, we go to the next question from Alim Yulianto from Universitas Lampung. And his question is about the development in the remote sensing such a satellite. Is there any big problem from government into the development that satellite from Lapan?
Problem from the government, or
He mentioned the problem from government. Maybe about for supporting the development.
yeah, okay, I see. Okay. Honestly speaking, there is not really a big problem. We know that the developing a satellite need a lot of facility and investment, right?
Yeah.
We know that of course governments have a lot of other priority. So what we are doing is, of course, as I mentioned to you, so we develop the satellite as much as efficient as we can do, but with very large usefulness that we can get. So that's the way how we develop our satellite so far.
Okay. Okay, Mr. Hasbi, thank you. So for the next question is, I think for the participant want you to spill about the costs from the government that has been given to development the satellite from Lapan. How much the cost?
Okay, Lapan budget, as you can see in our website, or you can see in the other sources. So the budget total of Lapan research and development, not only in satellite, is very small. The country, let's say we have about 50 million a year. Sometimes it's come to 60 million US dollar per year. But if you ask for satellite itself, it might be around 5 or less than 4 million a year, for example, including the salary of the employees and so on. And if you compare with other country, of course, we are small, but that's okay. I mentioned to you, we have to go on with all the things that we have so far, right?
Yeah. Okay. Thank you, Mr. Hasbi. So, for the next question is, are there any plan from Lapan to launch a massive constellation satellite for broadband access, just like Starlink and O3B? And if so, how's the roadmap of it? I think that's
this is very, very, very interesting and very good question. So, as I mentioned to you, we are as a government body. So what we are developing is for research purposes and also technology demonstration to all the stakeholders. And what we hope is the industry in Indonesia get this idea from what we are doing, and then they can do the business by having the development that we have done already. So, for example, now we have a program for having the constellation of satellite to monitor the Indonesia in 24 hours by having the non-GSO or low Earth orbit satellite. Let's say we need about 8 to 9 satellite, and then the roadmap is we will develop only one, and then once we launch, and there will be industry behind us that will take, or they will make another 8 or 9 satellite afterwards. So this is the idea that what we have. So we really encourage the industry in Indonesia and also their partner in another country. So I believe that by having this very strong relationship with industry, we can achieve the space industry in Indonesia.
Okay, thank you, Mr. Hasbi. And I think we will go to the last question because the time will run out. For the last question is, can Lapan satellite help our military tasks like to destroy OPM atau organisasi Papua Merdeka in Papua, or to find their central base? Because we know it is the easiest way to search them.
Okay, good question, but unfortunately, I cannot tell you in public way. So, yeah, I'm sorry that I cannot answer this question. Sorry.
Okay, okay, it's okay, Mr. Hasbi. Okay, I think for your section is done. Thank you very much, Mr. Hasbi, for your interesting and great presentation. Okay, I think before we go to the next tutorial, I would like to take picture together. Maybe a co-host or host, could you help me to take the picture?
Okay, let me take the picture first. Okay, I will count back to 1, 3, 2, 1. Okay, there's 5 slides. And then the second slide. 3, 2, 1. Third slide. The fourth slide. 3, 2, 1. And the last one. Okay, thank you.
Okay, thank you very much for the co-host. I would like to say thank you again to Mr. Wahyudi Hasbi. We hope your presentation can increase our knowledge and insight. So stay safe and stay healthy, Mr. Wahyudi Hasbi. Thank you. Good afternoon.
Thank you, Mbak Ulma.
You're welcome. Okay, we'll go to the next speakers. He is Professor Wataru Takeuchi. Good afternoon, Professor. And he is from Tokyo University. Hello, Professor Wataru.
Yes, thank you.
Okay, good afternoon.
Good afternoon.
Okay, so I would like to remind you, your time to presentation is about 1 hour, and we will go to the question and answer section.
Okay.
Okay, so time is yours.
Okay, thank you very much. chairperson, and good afternoon to everybody. Um, my name is Takeuchi. I'm from the University of Tokyo. And first of all, I would very much appreciate to give me a chance to talk on this tutorial. My topic today is infrastructure health monitoring with technologies. Okay, here's my today's content. This is tutorial, but it's rather more lecture style. I do not have any hands-on practice for today. So I prepared mainly four material to introduce SAR technologies, mostly for application side. And the first one is I talk about deformation of active volcano in Indonesia, which was done by my previous student, Indonesian student. And second one is land subsidence monitoring in Surabaya city. And also this is done by my previous Indonesian students. And third one is the structure movements of Japanese express highways. So we have some collaboration research work with Ministry of Construction in Japan, and then Highway Management Agency, and also with Japanese Space Agency and JAXA. And last one is this is not how can I say that the SAR technologies mainly use ground-based measurement with 3D laser scanners, but SAR investigation is still going. But we did some experiment in the bridge structure measurement.
Dr. Takeuchi?
Yes.
Yeah, presentator mode you can show. You show. Yeah, right.
Oh, okay. And last one is rather examples in Myanmar, which we have done in the last 5 years of research project. Okay. And this, I start from my talk from these figures. This graph shows the percentage of social infrastructures which has been built for 50 years or older than that in Japan. So in Japan, most of such social infrastructures like road or highways or tunnels or river management facilities or harbors, which was constructed in the early 1960s or 70s, since we hosted the last Olympic game. Then such important infrastructures, high-speed railway or highways, and it has a lot of large scale of infrastructures, has more than 50 years old. And so now in Japan, more than 50% of our budget expenses for the Ministry of Constructions for social infrastructures are used not for the new development, but mainly used for the maintenance for existing infrastructures. And most of those infrastructures are newly developed in, for example, Indonesia or Malaysia or in Thailand, which is constructed, which is newer than Japan. You also may have face some problems, such an aging problem of social infrastructures. And such social infrastructures are durability is very much depends on the quality of your constructions. So that because it needs such a long time span of service operations. So such proper maintenance is very much important. So remote sensing technologies, as well as such in situ measurement by different type of sensors or the wireless communications, and a lot of sensors are installed in the new newly established infrastructures. But on old infrastructures, we do not have such a proper management. So now remote sensing technologies, in situ measurements, as well as UAV, 3D laser scanners, bunch of geospatial technologies are very much highly expected to do some monitoring and to get some evidence which area needs more proper management or the prior management or to prevent such an accidents. And in terms of SAR data technologies, since the launch of first SAR satellite in early 1990s, and recently, this shows just one example, which is available in Japan. So the Japanese Space Agency is operating AEROS-2 satellite, which carries Pulsar 2 sensor, and which has 1 to 3 meters spatial resolution, and which carries L-band satellites. And this is a success of AEROS-1 and its predecessor of JS1. So we have a very almost 25 years of history to operate L-band SAR data. And if we see European countries, now Sentinel-1, 1A and 1B, 2 satellites are fully operational since 2014. And all of Sentinel-1A and 1B data are free of charge, which carries the C-band data. And in TerraSAR X or X standard, those X-band satellites, SAR data also available, but which is mostly commercial basis. And middle table shows the L-band satellite is mostly used for forested area, also such vegetated area, which has more longer penetrations into the land surface. And a lot of research has already done, and which was found that the movement of plates and land subsidence and landslides, the L-band is very much suitable for that. But for L-band satellites, because the number of satellites are very much limited, so we need to seek for other chances of satellites. Because L-band, for example, AEROS-2 cases, it has only one satellite. So we need to wait for another 2 weeks for the satellite to come. It's emergency operations cases, the more data is expected. But in case of C-band, then Sentinel has, for example, Sentinel-1 and 1A and 1B, it has 2 satellites. Then the revisit time is almost 5 to 6 days. So it's very much suitable for such emergency operations. But the C-band is more subjected to vegetations, as well as some very dense cloud coverages, same as X-band. So those wavelengths and the frequency and the spatial resolution and data acquisition cost and data frequency, all of those are in trade-off relationships. Then here in this talk, we consider how can we apply SAR technologies for specific social infrastructure applications. And then this also shows us some history, which I already talked to you. And then now move on to the first topic in the volcanic mountain activities in Indonesia. Because our test site was located in Mount Bromo, which is one of the most famous active volcano in the world. So you Indonesian people, of course, knows much better than me, but it has erupted several times in the last 20 years. And then those areas also I have been there. And then it's very surprisingly, so that local people live there, do some cropping, as well as many people visit the site as sightseeing places. And we also have our active volcano in Japan. And one of the most famous is Mount Aso. And it's we use our experience, what we have done based on the Mount Aso analysis. We apply the same technique for this Mount Bromo area. And the motivation for us is try to give some kind of early detection of eruptions. And of course, in the early detection of eruptions, so people say that the mountain itself seems to be expanding and could be observed as an uplift seen from the space. And how those phenomena can be monitored and those physical properties could be obtained by interferometry technologies. And also, for that analysis, we seek for the possibilities to whether or not we can detect of some symptom of eruption or some sort of forecasting to give an early warning for the hazard assessment. So we have mainly those two objectives for this study. And to cover the phenomena, so because this study was done in 2017, back to almost 10 years back at that time. So it has two eruptions in November 2010 and December 2015. So that those two eruptions were covered by two operational satellites. The earlier one, 2010, was covered by the first AROS-1 satellite and Pulsar-1 data, which has started its operation since 2007 until 2011. Then we need to wait for almost 3 years for the next satellite, which means AROS-2 Pulsar-2 was launched, then which covers the eruption happened in 2015. So those two different satellite and carries different sensor. So we need to combine both of these two different data set together. The main difficulties for Pulsar-1 was due to the orbit information was less accurate than that of Pulsar-2. So that to carry out PS INSA analysis or INSA analysis, we need a co-registration of different scenes. So that orbit information need to be accurate, and also to get a good baseline between the different sensors. In new sensors, AROS-2 or Sentinel-1, we do not worry so much about that. But if we try to trace back to before that, the earlier satellites have some technical difficulties in the co-registration of the images. And as a secondary data set, so we got some population data, a distance from such eruption point, also the land displacement inferred from PS INSA analysis, and land use land cover data set. Most of all of those data are obtained from ground measurement done by BIG. Also some land cover data provided by also BIG. Then in the data processing flow was rather simple, and we combine SBAS, small baseline analysis, because of AROS-1 data, those to get more coherence images. And then also we apply PS INSA analysis, and those use some time fund software to carry out very conventional PS INSA analysis with small baseline data set. And this is shows the results. And this figure graph shows the Mount Bromo. Mount Bromo is indicated in yellow color. And then left side, you will see the Malan city. Then the red point shows the forested area, and which is indicated as point A. Then the top graph shows point A in the forested area, which is indicated by red point. And x-axis shows the time from 2007 to 2011. And we have almost 14 scenes, 20 scenes of pulsar data. And y-axis shows the displacement in centimeters. And of course, this forested area has a matured forest. It does not have such drastic changes of forest itself. And as you see, variations of the displacement found in the forested area is rather small. And it's most, say less than 1 centimeters in a year. So that in 2008 to 9, it looks like some anomalies were found, but maybe this is due to some technical problems in the image co-registrations or something, but it's still regarded as within the era of acceptance. So we regard this displacement could be neglected, and we found this forested area measured in 2007 to 11, almost 4 years, has no displacement were found in this forested area. And next, second graph shows the urban area, which means a blue point shown in Maran City. And Maran City, from 2007 to 9, you will see very same kind of trend in the uplift of displacement were found, same as forested area, but which also could be we consider as neglected. But in contrast to forested area, urban area seems to have some land subsidence, some sort of subsidence, which means the negative displacement means subsidence. So distance from satellite to the ground become larger. Then start to happen in 2008 and continuously, gradually going to be down and down, and seems to have some substance, seems to be occurring here in the urban area. And the last one is the point C in the top of the mountain, which is in the Mount Bromo. And from 2007 to 2010, the displacement found in this point is almost 0. But in some significant change has been started, and looks like the positive displacement were found start from 2010 to 11 in the SAR data analysis, which is almost 3 to 4 centimeters in 1 year. So which we identify as which is corresponding to the eruption period. So we identify the significant changes were detected, properly detected with AEROS data analysis. The next graph shows the same analysis of results, result of analysis, which shows the displacement from 2007 to until 17. The first 4 years, 7 to 11, which is covered by AEROS 1 data, and 15 to 18 covered by another satellite, AEROS 2 data. Then as I explained to you, in the Mount Bromo area, positive displacement uplift were observed in 2010 to 11. Then very sad, but we have no observation data from 11 to 15 due to AROS was not launched. Then we did the same INSA analysis, 15 to 17. Then looks like some same kind of uplift trend were found over the time. And that means 15 to 17 operations, some uplifters were found, but maybe this is caused by the deformations related with the eruptions which happened in 2015. And such uplift deformation looks like almost 2 times larger than that of 2010 eruptions, which means almost 10 centimeters of uplift were found in 15 eruption cases. But this study is completed at this time because of time limitations for his research. And we continuously do this kind of observation with monitoring. Also, some early detections for the next eruptions. So this is the results of a first example of volcanic mountain monitoring in Indonesia. The next topic is land subsidence cases in urban area. So we selected Surabaya city in Indonesia. This is mainly due to the large subsidence is already reported, and which caused some damage in the infrastructures, such river banks or houses or the bridges. And also Surabaya city is the second largest city in Indonesia. Then the BIG has good geodetic measurement network, also a GNSS navigation satellite data analysis over that area. So that main objective was very similar to how can we apply INSA techniques to get the spatial distributions, which locations, and has more deformations. And then to investigate suspected physical factors which cause the surface deformations in Surabaya city. And this graph shows the rate of subsidence which is obtained by the geodetic measurement in the in situ measurement. So now in the city, in the downtown, so I'm very sorry that I probably those 4 characters denote some location or land cover, but those RKUT, which is located in close to the sea shoreline area, has the largest subsidence over these regions, almost 3 centimeters of, per year. So this is a ground survey we have done. This handsome man, and his name is Mr. Arif, is a government officer in BIG, and he has done intensive field measurement. So we visited so many places, and mainly those subsidence was caused by the groundwater extractions. And we visited so many places, and such subsidence has been studied most, according to the interview, most studied 10 years back. Then subsidence was accumulated year by year. And in some cases, ground become lower than accumulated more than 10 centimeters then centimeters or more than 10 centimeters of land subsidence cause some physical problem on the structures of the houses. Also, the lowering on the gap between the road and houses. So in rainy seasons, usually happens the flood water go inside the houses, and which cause many problems in the regions. And I was really surprised such the groundwater extractions is still ongoing. And I'm not so much sure this is officially accepted or not, but groundwater extraction such subsidence happened in Japan also in 1960s or 70s. Also happened in Bangkok, for example, in Thailand, in early 1980s or 80s or 90s. But because of people need to, population of Indonesia is expanding and urban area also expanding, and such subsidence is reported, and not only in Surabaya city, but also Jakarta city and many parts of the cities. And this is a preliminary study which try to indicate the perpendicular baseline, the baseline between two different orbit of satellites. And in Pulsar 1 cases, and you will see baseline, baseline, perpendicular baseline is most, with reference to the base master image. Then slave image, you will see, say, 1 to almost 2 kilometers of perpendicular baseline were found. So that temporal Pulsar 2 cases, as you see in the below graph, then baseline is, say, almost 1/10. It's larger one is, say, 150 meters, and usually within plus minus 50 meters. And in almost 1/10 of the smaller baseline were found in Pulsar 2. And this parameter could be very much important, which be impacted on the small baseline analysis and the spatial correlations among the images. Then the more coherent, we have more chances, smaller baseline has more good analysis to get the more coherent data and more point on the PS inside analysis. Then this graph shows the time series of analysis of Pulsar 1 data cases. And this map shows a spatial distribution of subsidence in Surabaya, over most of Surabaya city. And green color, green shows the almost zero, no changes. And blue shows more negative changes, which means the subsidence. Then we plotted to extract 4 points over different land uses. So the point A stands for residential area, and which is more close to the sea area. And point D also residential area. And point B shows the industrial area. And point C shows commercial area, the business, maybe Kota area, business, central business district, downtown area. And 4 graphs shows displacement over different locations from 2007 to 2008. So 2020 means that this is 2008 February, start from 2007 January, February, almost 1 year. Please understand, very sorry that this the ticks has some problem, but please understand 2007 January to almost 1 year of analysis. Then over residential area in 1 year, negative displacement were found as in almost -2 centimeters in 1 year. And same as industrial area is a bit larger, and commercial area is much more larger, and residential D has much more larger. So that in avalanche, the overall trend of subsidence negative displacements were found over all region of the Sulawesi, and this displacement was almost 2 to 3 centimeters per year. Then if we going back to the previous ground measurement analysis, the ground measurement sense most, of course, it depends on the locations, but largest displacement were found in most nearly 3 centimeters. So looks like were reasonable results. And this result shows Pulsar-2 data analysis results, and which shows most 2 years from 2015 to 17. Then line of sight vector changes shows green, red color shows almost 0, and yellow to blue gives more bigger values. So as you will see in the indicators indicated in the more in close to coastal zone, and which is denoted as blue color, and which shows most say 10 centimeters. The displacement will be accumulated and more in Pulsar-2 analysis. So we compare this analysis, because some GPS measurement, maybe not GPS and some GNSS, not on GPS, but other maybe positioning satellites data set were also merged together. And we compared with INSA measurement displacement and GPS measurement displacement. And blue point shows the displacement found detected by INSA analysis, and red color is those of GPS. And it covers only 3 years, but still have some discrepancies. But overall, the trend shows very positive relationship between INSA analysis and GPS. So that although it has some bias, then we need to be corrected. But such with reference to GPS analysis, then INSA analysis could have more benefit, because INSA analysis, if we have successfully detect the permanent scatters, then we could get the displacement as a map. So that if new building is constructed, or some example logging, some forest was lost, so in that such above ground biomass, above ground structures was changed. So in that case, analysis cannot be achieved. But if the same permanent scatters, same building is there, then all the displacement was caused by land itself. Then over such area, such we could give analysis. Then such information could be shared with the necessary government management for the steps. So this is the end for the second part. And the third part was in Japanese example, which is done in the Ministry of Land and Infrastructure in Japan. And they try to apply remote sensing technologies to investigate such deformations, which usually happens in the mountain area, in the high-speed roads or the highways. Because in the construction of high-speed railway or high-speed tollways in Japan, in urban area, because we have no mountain, but if we need to construct such railways or tollway in mountain area, so we need to do some constructions. Then we need to cut off the soil and remove the soil. And sometimes we need to construct a tunneling. So in that case, that land and soil was removed, then we often have such deformations, which is caused by the land itself will be distorted. Also, another case is if we construct such large structures in the area where it used to be at the cropland. For example, rice paddy field area, we used to have a lot of rice paddy field, and then some area become fallow land. Then such rural area, government built up tollway. Then such soil stiffness for that area is not so much strong or suitable. Then we built up such large structures and the bridge basement. Then those bridge basement do not have enough support by the soil structures. Then will be easy to be a subsidence happens. So usually such road managers or the planners, managers need to do such measurement by the field survey, by the conventional survey. In Japanese cases, in the national road, we call the kilopost. Every 1 kilometer, we have such measurement. And as a government have a law, need to report every 1 year. Every year we need to give such displacement and the deformations. And if such deformation happens, then we need to overlay the asphalt and try to make the road surface very much constant. But problem is that we have technology and using such very conventional method. But problem is the maintenance cost. And then some of, if the road is stable, then do not need such frequent measurement of surveying. But if such area, which seems to be very much doubtful, some subsidence happens, we need to give more measurement more frequently, try to know the trend more often with a low cost. Then seek for the possibility to use remote sensing data. Because remote sensing, example, Pulsar 1, Pulsar 2, usually covers 50 to 60 kilometers of area wide. And 50 to 60 kilometers is much larger than that of kilopost. For example, kilopost cases, it contains 50 to 60 kilopost. Then in conventional surveying, such pairs of measurement usually takes few hours for one measurement. Then we need to block the traffic mostly nighttime, then do such measurement in nighttime because daytime so much traffic is there. But if we use satellite data, then do not need to block the traffic, also can cover very large area. But probably the accuracy for the measurement is less than that of conventional survey. So that try to check the balance between the cost benefit and then accuracies. This is what they try to do. And nowadays, such managers, construction managers has a maintenance car. Though those cars, like a Google car, carries a 3D laser scanner, also photogrammetry, and so many the images. Then they're called MMS, and then they carry run about run over the area, then collect so many measurements. Then conventional fixed ground survey and 3D laser scanner carried on the car, and remote sensing measurements. Those three are synthesized together to get some symptom of early detection of such deformations of structures. Now, this is a kind of background. And then so we have some test site. And usually such construction managers database is not open to public. So we gotten some difficulties, cannot open all the data to the public. And this is Japan Island. So we have several sites, and you will see Abuta. Abuta is very close to the active volcano, and which erupts every 20 years. And second one is Sakata. It has a tollway, which is constructed on the rice paddy field. So that in Japan Sea area, the soil is not so much suitable to construct such big infrastructures because of sandy soil. And the third one and fourth one are located in the west part of Japan, in the mountain area, and which did a lot of excavations. Then such deformations were observed. And first example shows the Abuta area, which is close to the Usu Mountain. This is like a Mount Merapi and active volcanoes. So that just very close, just few kilometers far away from the mountain, there's some expressway from Sapporo to Hakodate. And it is also a snowing area. And then winter season temperature go down to -20 or something. And such very tough due to temperature changes. And then also which cause some very much big damage on the concrete structures. And this line shows the expressway. And below graph shows the INSA analysis. And red color indicates the uplift trend inferred from the INSA analysis. Then this is zoom in. Then this green line shows the highway line. Then surrounding area, highway itself seems to be okay, but surrounding area looks like something happened in that area, which cannot be accessible by the field survey because this is covered with forest. So that we found something happening is there. Then okay, that other area seems to be okay, but this area might have some land subsidence, which some deformation were found. Then land subsidence could be, or landslide may occur over that area. And also, you will see that some compared with ground survey, then some uplift trend were found. So that the managers, the road managers side then can identify, it is very good news for them. It looks like some evidence was found. Then usually they can check the deformations just on the road surface by the conventional 3D radar scanners or survey. But satellite indicates more larger areas might be affected, then which cause some damage in the road. Then second example were the highway over rice paddy field. And in this case, we have no mountain and no variance because this is a tollway. And then over this tollway, so as I tell you, this 155.3, 152.1, which indicates the kilopost. Then from satellite, even satellite spatial resolution is 10 to 20 meters resolution. but it's much finer than that of conventional surveying, because conventional surveying, they do surveying every 1 kilometer distances. So that from satellite analysis, PCE analysis, so we could map the surface deformation of tollway, so every 20 meters. So we give different colors based on the substance, and green color shows no substance, and blue color shows more larger substance. And you will see, and some large substance were found in this region and these regions. And usually those large substance were found which is far away from the bridges, because this is river, and then those white color, very sorry, written Japanese, those white characters shows the location of the bridges. So usually bridges has very strong structures, and which has a very deep pile to support bridge structures. So usually bridge does not have no deformations, but in between the bridges, we have no such strong pile deep into the ground. So probably large displacements were found in between the bridges. So that all of those KP stands for kilopost. Some kilopost, for example, 150.9 kilopost, which is far away in between the bridges, which has no supporting pile, looks like has deformation continue to happen there, and then which has good agreement in in situ measurement. In in situ measurement, in 10 years, from 2004 to 2014, almost 20 centimeters of displacement were reported by the ground survey. But due to limited availability of satellites, we can cover only 4 years by pulsar data, but a very similar trend were found. So with reference to the in situ leveling measurement, such as I explained in the Indonesian survey cases, then we could do some bias corrections if we have such ground data. Then satellite data, we can give more continuous, spatially continuous data, and could be indicated that could have some potential to do some assessment, which has no change and which still have some changes. Then if some such changes were detected by the satellites, then load managers can identify which has more suspicious area, and no suspicious area, maybe just let as it is. But more suspicious area, they think about to increase the frequency, more frequency checked by the ground survey. It's something like that. Then speed up and also reduce the cost of maintenance of measurement itself. And the last one is such mountain area, which is covered by some excavation was done. And this is a load, and some substance were detected in the area of deformation by the in situ measurements. And this is a bit far away from the load itself, but may have some effect. Then such land substance, the land substance could be an indicator of landslide for that area. And but problem is in the ground, in the surrounding area. So they have such concrete anchorage is there, but those deformations also disturbed by the existence of vegetations. So they clear cut the vegetations once in a year, such weeds or some grasses, but it's usually in Japan, such grows up speed of vegetation is very fast, so that which cause some problem on the even L-band sub-data, such surface deformation results could be disturbed by the existence of those vegetations. And we tried by the C-band analysis in Sentinel-1 data, but it was very difficult due to C-band is more shorter wavelengths. It's more influenced by the base stations. And the same as this is not good example, and we did such measurement, same analysis, but the satellite has no agreement with ground survey. Probably this is due to main two reasons. First one is those base stations, and second one is direction of the load itself. Because satellite orbit direction we cannot change. Right? Satellite always come from north to south or south to north. So if it is perpendicular to the satellite path, such directions is relatively bit difficult to identify such deformations. And but anyway, such harmonized with the mechanism of landslide, which is done by the surveyors, then satellite measurement can be integrated together. Then such mapping is very much effective. But applying for satellite technologies, we need to consider the orientations between the satellite path and an orientation or direction of the load itself. So those were the findings of this. And also we need to consider the such geometry between the satellite and the orbit, satellite orbit and the location of ground object. And because those deformation we got is just simply in the direction of line of vectors. It is not exactly the same as horizontal and vertical. And we need to know the both horizontal, decompose the deformation into from line of sight vector to horizontal and vertical. We need to combine two orbits, both in ascending and descending. And here I cannot show you the 2.5 dimensional such decomposition method, but maybe you can refer to the other journal papers, which is open to public. And now if we combine so many different of satellites, then such decomposition also can be achieved. And maybe last one, I have only maybe 5 minutes to go, and to apply such suspension bridge monitoring with remote sensing. And this is we have done in the project in the very large span of almost 300 meters of span over the bridges in Myanmar. And then usually they use such conventional surveying. And then we carry photogrammetry and 3D laser scanners, and which can be used as a reference from some inferred from satellite. And because of such anchorage to the rope, this anchor was not so much strong, and the basement has some problem, and looks like the main tower of the bridge looks like inclined. And of course, Myanmar does not, this location is a bit far away from the fault line, but if such earthquake comes, then the bridge will collapse. And then almost 2 years ago, one bridge were, how can I say, collapsed. This is not due to the earthquake, but the main anchorage was born. Then the rope was broken. Then the bridge fell down, and few people died. So we seek for the possibilities to whether or not to check such a main structure. Some detection, early deformation could be detected or not. So this is done by the SATREPS project, and which is under the collaboration between JICA and JST. And we have done the research with Myanmar and Japan team. And the 3D laser scanners we surveyors usually use such laser scanners. And these laser scanners used to be, cost was very expensive, but in the last 10 years, the laser scanner cost become almost 1/10. So that we, even university laboratory can buy such laser scanners. So we carry this and do measurements. And also conventional SFM either can be done from ground photos or UAV. So we did the conventional SFM. Whether or not can be checked such tower inclinations or the hangar inclinations and the technical limitations for that. It was done almost 5 years ago. And probably nowadays more the spatial resolutions of the camera or the scanner become much more higher. Yeah, then the processing, we follow very conventional style. And then the main tower is almost 50 meters high. Then the span was almost 300 meters long. Then location was the Yangon city, Rangoon is here, a bit 200 kilometers far away. This is an alluvial soil area, and then rainy season is totally flooded, and it's very far away, takes time. And then such long span bridges we found around those locations. And then we did such measurements. And finally, we got such point cloud data, then put into the BIM. And such deformations, BIM data was integrated with an FEM analysis, finite element method, and such a structure analysis, and then back trajectory analysis can identify which location of the portion of structure could be damaged. Then finally, then we did a lot of measurements, both from photogrammetry and 3D laser scanners. Then we found almost 40 meters high, then in the top of the structure, nearly 20 centimeters and 15 centimeters were found. So north and south, that means, looks like this line means that the structure is bending toward the river side. So that if this inclination is accumulated, it's very dangerous, like this. And this is another example. It's like, and in this case, those hanger ropes were also measured, and like 20 centimeters cases, some cases, but in some hanger cases, very much less. But such different type of displacement were found in different location of hangers. Then now we try to combine those two measurements from remote sensing analysis, but still ongoing. And then now we can combine such UAV-based SFM, 3D laser scanners, and hopefully remote SAR technologies, remote sensing SAR has more frequent continuous operations, then can merge together with such BIM analysis. I think time has come up. Thank you very much for your attention.
Okay, thank you very much for Professor Wataru Takeuchi. Okay, before we are going to the question and answer section, I would like to ask to Professor Wataru Takeuchi. Actually, I have now I'm doing my research about investigating surface deformation in Surabaya. You know, right, that Surabaya is best struck by active fault. Maybe you ever hear Kendeng's fault. Yeah, so my question is how much the optimal amplitude dispersion to produce the good coherence of point scatters in PS insert processing, especially to investigate the lens subsidence in urban area.
Oh, thank you very much for your question. So your question is how many images we need?
The optimal amplitude dispersion, or maybe coherence threshold.
Coherence.
Yeah.
Coherence is, it depends on the image analysis, but in Slava cases work well. I think coherence, maybe 0.3. I think.
Oh.
Yeah, 0.3 is maybe, is maybe good enough.
Okay.
But in such mountain area where the vegetation is there, they may coherence maybe go down to 0.1 or something. Seems difficult.
Oh, I see. Okay.
Yeah, yes, thank you.
Okay, thank you, Professor. So I think we're going to the question. I will share screen. So we have a question. So for the first question is for land deformation on active volcano, especially in Bromo Mountain, until 2020, did you compare it with other data or references? If yes, using which data or references?
Oh, thank you very much. Other data means other satellite data analysis?
Yeah, maybe.
Satellite, we do not, we did not do any other satellite. We just do only Pulsar 2 data at that time. And compared with ground in situ measurement, satellite is only Pulsar 2 data. Of course, at that time, 2017, not so many Pulsar data, Sentinel-1 were available at that time. So maybe some comparison with Sentinel-1B, 1A and B are very much interesting, probably. And for urban area, probably C-band analysis also should be okay.
Okay, I see.
If land deformation is not that big, because C-band is almost wavelength 6 centimeters. If land deformation is much bigger, then maybe unwrapping processing doesn't work well. But it's very important point. Thank you for your question.
Okay. Okay, thank you, Professor. So we'll go to the next question from Rauda Hawin Ayani. She's from Master Student Institute Teknologi 10 November, Surabaya. And his question is, what kind of correlation data between INSAR and GPS? Maybe about the how to validate it and how to combine both of the data.
No, we just simply plotted.
Or just
as
simple as simple.
But remote sensing data cases, because Pulsar cases, the footprint is 10 to 20 meters, but the GPS location is just 1 point. Then remote sensing cases say one footprint include so many different type of, in our case, 4 or 5 housing included in one footprint. So that if you choose such very much complicated locations, or some building was lost or newly constructed, if you choose that pixel, may have some problem. So you need to pay attention for that.
Okay. So, Professor, is it possible to convert from loss in SAR to vertical displacement in GPS from GPS?
From GPS data that the GPS data we got is I do not know exactly, but for remote sensing data, we did not do any such vertical or horizontal, just line of sight vector data only.
Yes. Okay, I see. Okay, thank you, Professor. Then for the next question is between the wavelength of the L-band, C-band, and X-band of satellite, which one is wider range and more efficient to use in remote sensing?
It depends on your purpose, I think.
Oh yeah, that's an answer.
But in our Japanese case, for such road infrastructures or highway monitoring, usually in the surrounding area, we have some vegetations, so that we have no other option to use L-band. We tried C-band many times, but C-band is very difficult to get a good coherence data.
Yeah, that's right.
So we expect a lot. In some area works well, but some it's very difficult.
Yeah.
And usually L-band is very suitable.
Yeah, because I use the C-band too, so I think it's so limited. Yeah. Okay, Professor, I think that's the question again. Yeah, I think enough. So thank you so much, Professor, for your time. Such an honorable to meet you here. So we hope your presentation can increase our knowledge and insight. Okay, thank you so much, Professor.
Thank you very much.
Yeah, you're welcome. Stay safe and stay healthy, Professor. Okay, thank you. So we're going to the last speakers.
Okay.
Hello.
Hello. Nice to meet you.
Yeah. So for the last speaker is from Professor Higuchi Atsushi.
Yeah.
Yeah. How are you today?
Can you hear my voice?
Yeah.
Okay, I will try to show my presentations. Can you hear?
Yeah, BNC.
Can you see? Yeah. Okay. Yeah. And first, and nice and please and relax to watch my presentations because I don't talking about the SAR. Yeah, because this is a geostationary satellite. So yeah, and please enjoy. I will show the movies captured by the geos. So okay, let's go ahead. And I will be talking about today's topics. Okay, firstly, I'm talking about brief introduction of the geostationary meteorological satellites, its principles of how to measure its things. And the next step, I will be talking about the third generation geos. This is a current and updated the geostationary satellite. And I will be talking about how advanced compared with the second generations. And the second is what kind of event can captured by the third geos. I will introduce by the movie captured by the mainly Himawari. I will show the movies. And the third one is I will talking about how utilized. I will show some examples by our group's research results and some review results. Finally, and I will be talking about the closing remarks about the third geo utilizations. So you know, there's so many satellite captures and around the Earth, and approximately its height is approximately 700 and 800 kilometers above the surface. And this is and polar orbit satellites, many polar orbit satellites you can see. On the other hand, and another satellite can capture the Earth, so-called geostationary meteorological satellite. And so many satellites also covers whole of the Earth, like this. This is, and according to the WMO's space program, WMO means the World Meteorological Organizations. This is, and combined with the meteorological agencies to capture the weather. So this is and other opportunities. Okay, so this spatial resolution is based on the altitude of platforms. So many and satellite observes around the 700, 800 kilometers. This is a kind of the height balanced to the gravities. And most of stars observes around this height elevations. On the other hand, geostationary satellites more higher its height.
And this height is so many higher compared with low elevation satellite. This is also balanced with the gravities. So I will explain this and phenomena in the next slide. So this is a kind of schematic illustration photograph. This is Hammerslow's player. He is us. Please imagine, he is us. And Hammer itself, this is a sensor or this is a satellite. He is rotate like us. So, and here and this Hammer has the cameras. This Hammer always sees the face of the Hammer player. Always the same face. And this camera can see. Then captures images like this. Whole Earth can captured by the geostationary satellites with the same face. You can see like this. So this is a good advantage of the geostationary meteorological satellites. Always can capture the same face of the Earth, but so far from the Earth. This says that spatial resolution is not so good compared with low elevation satellite. But its advantage is and geo is frequently observed compared with low elevation satellite. In this case, it combines the 4 geostationary satellite, and FY2D is operated by the China's, MTSAT-2 operated by the Japan's, and GOES-11 and GOES-13 is operated by the USA. This is a 3 hours and integrated movies. It's so very easy to see the movement of the cloud. And generally, and brightness temperature is a more colder area represent the cloud. So to see that these movies can easily to imagine where is the cloud, how to move the cloud with the high temporal resolutions compared with the low elevation satellite. This is a big advantage compared with a low elevation satellite. So, and the next slide shows the typical channels in the geos. And the first one is that I so-called the IR1. This is 10 micrometers. This is a window of the atmosphere fields, and the center wavelength is emissions from the Earth. This 10 micrometers wavelength observation is related to the surface temperatures if the cloud-free areas. On the other hand, the cloudy area is captured by the low brightness temperatures. So these things say to the tropical region is a high cloud and observation, high cloud areas can capture. It's easy to see to the cloud movement. So widely this is applied to the TV program, typically in Japan. So everybody knows. And the next slide shows this is a water vapor band. This is 7 micrometers. This is all second generation geos to diagnose atmospheric flows via water vapor contrast. This is absorption band is water vapors. So this says that and very high density water vapors occurs related to the cloud or precipitations areas. These stems and intercepted by the water vapors. So compared with the 10 micrometers movies, it shows and more how to say the gray colors image, and say that to say the black area, darker area means the relatively atmospheric condition is dry. So to see that this compares to 10 micrometer and 7 micrometers compares two image. And the 7 micrometers image can easily to monitor how to move at the atmosphere's motions and dry and moist air's contrast. So here is and the tropical area's upwelling motion is dominant. In the subtropics, this is a substance of the atmospheres, and relatively the dry air mass can capture. Such a thing can easily be monitored here. And other one is the shortwave IR. This is 3.5 or 4 micrometers. This is and both solar radiations and Earth emissions radiations overlapping. So this means the day and night brightness temperatures difference also observed day and night and day and night. But and visible wavelengths cannot see during the night times. But these wavelengths can both day and night captures. This is one of the advantages in the shortwave IRs. And this is carried on the empty sat and the previous satellite of the Himalayas to the monitor's warm cloud. This is sensible to the waters. This is case. Okay. So such of things as generations and distinguish the generations of geos. And the first generation is the geo is only the one thermal infrared and one visible, only two channels. And the 2.5 or 1.5 generation is one and the TIR and one water vapor channels and one visible. And the second generation is a 2 and the TIR. This can apply to the split windows technologies. I will show later. And one water vapor and one visible. So, and the second 2.5 or third generation discuss, I will show the later. And this observation is a long history since the 90s. Here is and blue color shows the first generation. In the orange colors indicating the second generations. And this pink color shows the third generation satellite. Widely covers the whole of the Earth. So such of things can improvement observations since the first era to the second generation and third generations. So, and the next I will talking about how to utilize geostationary satellite and the detection of convective activities cloud by thermal infrared. This is a very basic things. And the detection of low-level clouds by the visible wavelengths is the next step. And the third one is I will show the combination of the two channels of thermal infrared to apply to the split windows technologies. This is also basic technologies. So first one, I will show the global distributions of the frequency of the thermal infrared threshold, a percentage of the cloud covers. This is maritime continent is the highest coverage of the cloud covers. This is very useful to the monitor the frequencies cloud covers. But some part is not so wrong. For example, the Tibetan Plateau is this is a relatively high coverage, but this is maybe wrong because of winter time surface temperatures also reduce temperatures. This is maybe misdetections. Also, Siberian area is some part of the misdetections. This is not so good point. So, and the next step is and how to utilize the visible. This is and two images, and this one is a visible image and zoom up. This is the thermal infrared image zoom up, and blue colors and area shows both visible and TIR can detect as a cloud because this is a high level cloud observed. On the other hand, here is and red and circles area is in the TIR case, it's hard to where is the cloud. But on the other hand, visible images, such kind of small patchy cloud can captured by the visible imaging. These things, the visible and image can easily to capture the low-level cloud compared with the thermal infrared. Because of the thermal infrared, the temperature difference between the surface and the cloud is very low because of low-level cloud. So in such case, visible and wavelengths is very useful. So, and this is one example, the whole area, whole period of the GMS5. So the cloud coverage detected by the visible. And here is the tropics and subtropical areas. And you can see that here it shows ITCZ likes high cloud detections. And over the land is a very orographic cloud can capture. On the other hand, here is this and figure shows the relatively lower compared with all cloud. We applied this and reduce and the cloud amount due to the split windows technologies. Utilize the two thermal infrared bright band difference. This is a good example of how to utilize the split window technologies. This is and Shimoe eruptions. So here is the thermal infrared movies, and here is the split windows. This split window means IR1 minus IR2, and 11 micrometer minus 12 micrometers. This thing is a materials emissivity difference between the cloud or eruptions matters. So in such case, the Shimoe eruptions. Please watching here. Okay, now here's. So, and very easy to distinguish the cloud and eruptions matters. Such of things very utilized the bright band difference between the neighborhood, 10 micrometer or 11 micrometer, 10 micrometer minus 12 micrometers. These things can capture also the optical thickness matters of the cloud. Such of things are very useful information for the geostationary satellite. So, and we are one of the center of the climate research. Now we are collaborate in Japan is 4 institutes or centers to the tackle with climate research. So our center and Center for Environmental Remote Sensing CERES is a satellite center. So we currently archiving the whole of the world's the geostationary satellite data and also data processing and from the raw data into the gridded matters. Yes. So this is skipping here. So currently, we have so many satellite data, geostationary satellite data. For example, the Himawari satellite, we are archiving from the start of the GMS1 to the latest one, Himawari 8, more than 30 years on years archiving, and anyone can access the dataset. For example, this is a GMS5 to the MT sat. You can visit this FTP site free of charge. You can download the data. Also, we are archiving the FY2 in the Chinese satellite. And also, we are archiving the UMETSAT satellite. But this is a restricted servers access due to the UMETSAT data policies. And also, we are archiving the GOES satellite. And also, this is free of charge. Any data you can download for the research. This is one of our activities. Okay, and this is an introduction, brief introduction of the GEOS. Okay, let's move on to the third generation's GEOS. This is the latest versions. So, and Himari 8 is the first and image of the third generation's GEOS, and compared with the previous one, MTSAT. MTSAT have the 5 channels, 1 visible and 4 IR band. But the currently is and Himari advanced Himari imager have the 16th band, very close to the MODIS type. And for example, the visible splitting the RGBs. This means the true colors RGB composition can be applied. From monochrome image to the color image can generate. And thermal infrared area is many channels, many bands increased. And also, I will show this, I will demonstrate later, and water vapor absorption band around the 7 micrometers in this, and slicing the 3 band. This means the color composition, and this is a water vapor's gradient, also captures here. So such similar and improvement was occurs. Here is the MODIS measure band. This is a NOAA's BS and JAXA's SGLI. And this is will be and launched is the 4th generation with UMETSAT, MTZ 3rd generations, and goes advanced baseline imager. And also Himari 8 AHIs have the 16, most of them have the 60 or 40 band. So this is band is very similar to the MODIS. So it says another word is, and currently 3rd generation GEOS data can utilize as a MODIS type analysis with fine time resolutions. So this is a time resolution is represent, and full disk scan is every 10 minutes interval. Very high frequent observations. In addition, the full disk scan is in the case of Himari 8, Japan area is 2.5 minutes and distributions. In addition, in the target area is a typhoon or etc. is also captured by the 2.5 minutes. Very fine time resolutions observations will be done. This is a great improvement compared with the previous 2nd generation of GEOS. Okay, I'll show the movie. So firstly, this is a full disk scan mode with the Himari 8, and daytime, nighttime is merging. This is currently the nighttime mode in the thermal infrared. And the daytime mode is the RGB true colors composition. A very beautiful image can see from the Himari 8. So also, these things can be captured by the GAUSS R and GAUSS S and advanced baseline images. Daytime and nighttime mode captured like this. And here is this is a GAUSS and 17th, GAUSS S. So very beautiful. Can capture like this. So, and please enjoy that this next one is a Kalman vortex captures by Himari 8 AHIs. So this is a very interesting phenomenon in the atmospheres. And Kalman vortex is and relatively stable conditions. It sees the beautiful patterns in the cloud. This is 1 day situations. In the next days, this pattern will be changed. Very beautiful. So this is largely depend on the vertical profile, the atmospheric stability, and the wind speed. So it seems very interesting and very beautiful cloud formulations can captured by the Himari 8. Okay, next things and many gravity waves triggered by the convections observed in Australia. So this is a summary infrared 10 minutes and intervals image. Can you see this kind of and wave propagations? Like a wave and triggered by the convections. Like here's, it's hard to see. Here's, like movings, propagate from the coastline to the ocean like this. Such kinds of 10 minutes intervals movies. So many is wave. You can see. So such of things is also captured by the Himari 8. This is simply do the 10 minutes high time resolution observation can easily visualize such kinds of phenomena. Okay, let's move on to the next images. So this is the RGB composite, is a water vapor's 3-band. This senses that and the 3 bands and Himari 8 is a water vapor band splitting the 3-band. So this meaning to the RGB compositions is applied into the water vapor band. So to easily to the monitor the air mass difference due to the water vapor's difference. This is the frontal activities. So here is a dry air mass. It's coming. And here is a color is different. Such kinds of color difference due to the air mass difference. This is a typical and mid-latitude movement, frontal movement can see. This is warm front, and here is a cold front. It's not familiar as maybe the tropical peoples, but and here is a dry and cold air mass, easy to visualize. So such of things is very interesting due to the splitting the water vapor band from the 1 to 3 channels. Okay, next is applied to this is a typhoon case, but a very rare case is movings from the eastward movings. Oh, sorry, westward movings around Japan. This is a rare case. So this is a typhoon and 12, number 12 in the 2018. So this is RGB composition of water vapors. So the red arrows area is a kind of the low. This is and the trigger is a movings. The typhoon from the moving like this. So this such kinds of the atmospheric composition and conditions difference easily to captured by the water vapor splittings because of the air mass difference easily to visualize like this. Okay, let's move on. So on the next two slides, two movies, and very interesting phenomena is the full colors and true colors RGB images. The first one is the forest fire in Siberia, and this is a transport case. This case here is dust, and mainly due to the Siberian forest fire. Can captured by the Himari 8. Okay, please wait a moment. So I cannot skip. Please check carefully. Watching here. You can see. Yeah, moving this is a dust air mass above the cloud. Here. So such of things can capture by the full and true colors RGB movies. Okay, next is very interesting. My favorite movies. This is forest fire in North Korea. After that, atmospheric environment drastically changed due to the forest fires. Anyway, start here. So here is a trigger, is a forest fires. In the next days, forest fire oriented smoke transport around here. In the case of Japan, is smokies, and here is very interesting phenomena around here. Watching here. So now it's the changes the aerosol into the cloud. Aerosol particle is in the seed of cloud. And also next days, very smoky environment. Due to trigger is the forest fires and the low-level cloud generated mainly due to the forest fires aerosol seedings. Such kind of the changing environment, atmospheric environment, very precisely is captured by the Himari-8. This is the performance of the third generation GEOS. Okay, one more, please. So start is this is forest fire triggers. In the next days, atmospheric condition is very dusty. And also, here is the dust will be changed to the cloud. Now it's changing the cloud. Also next days and hazy condition is still keep and the low level cloud it's so generated. So such kind of the environmental change and easy to monitor by the Himari-8. Mainly the RGB conversion full colors image is very powerful to this. Okay. So and now and our center, Chiba universities have this big displays and 4K displays, 6 tiles 4K displays we are installed and Quash real-time image movie can display in the Chiba universities. And also most of the movies you can see the YouTube site. Today I show the movies, you can check this YouTube site. And Dr. Toyoshima is and movie editings. And very interesting movie you can see the here. And also, and you can see that now real-time web and developed by the NICT, National Institute of Communication and Technologies. This is so-called Himari Webs and Himari Real-Time Webs. This is a kind of interactive website, and you can see the current and now and web and the past and image with the fast response. So, and please visit this and website. I'm also the contributor of the real-time web. And here's. So, and for the research, and we want to the changes raw data into the more and utilized data set like this. Geo collection is very important issues. This is an original data. This is a collected data. And we developed this and collections algorithm. Then this is published papers. And we use and Himari standard data, the full disk data into latitude, longitude, geo-collected geo and gridded data. So, and you can see that here is release note website, and you can download all channel, all band data gridded and format, and from this FTP site. And for the research purpose, and with a 10-minute interval, all data you can download. for research. So, okay, I will show the several examples. The one is very familiar with how to utilize fine time resolutions. So this is a case is a 2.5 minutes observations around Japan, and this is a 30-second observation. The phased arrays weather radars. Three-dimensional structures can capture by the phased array radars. This is fine time resolution. Both two images can capture the fine time resolutions to say the better understanding the behavior of the precipitatable cloud. So we combine the Himari data into the optical information, effective radius of cloud and liquid water path and cloud optical thickness and the cloud top height estimated from the Himari 8 data. Then we are one cloud and captured from here. The upper panel, upper figure shows the optical parameterizations of the Himari 8. And the lower one is captured by the phased arrays weather radars. This red line indicates the first echo detection times. This time is synchronized. So just before the radar's detections, cloud developings can be captured by the Himari 8. This is a cloud water's color and green lines increase just before the first detections, 20 minutes before cloud development captures, like this. And also optical depth in the red color indicates also increase just before the detection of radars. And also you can see this is a rain cells and downward movings can captured by the radars. And also these things synchronized with a visible wavelength reflectance reducing like this, very synchronized with well. These things, Himari also captures one cloud evolutions compared with the fine time resolution of stationary data. To say another word, to improve the understanding the cloud behavior by fine time resolutions. This is a very big challenge. And we are doing this research like this. And the next step, and we are estimate the rain rate is machine learning. The Himari data and already published paper is like this. In this case, we are learning machine learning, the random forest method, and the data itself estimates rain rate from the Himari 8. So this case is the estimate, our algorithm estimates rain rate. This one is radar amethyst, and in radar's networks observations, line-shaped rain rate, high, extremely heavy rain observed. But these things are relatively low cloud. It's not so good for the optical sensors, but the multi-channels data improves the accuracy estimations. As evidence, this is our estimation with only the one channel cannot represent the line-shaped precipitations, but multiple channels can estimate like this. Such of things as how to utilize the water vapor channel is very improvement. This is the difference between the 6.9 minus 7.3 water vapor channels difference. This is very good indicator of the rain rate behaviors. This says that atmospheric motion is a relatively dry air mass coming up airs. Such kinds of situations can recognized by the water vapor channels. Then our estimations is improved. Yeah, such of things can be presentable with the water vapor channels difference and the thermal infrared bands difference. This delta TBB's 10.4 and 12.4 differences the cloud optical thickness parameters. Here, and here is also the and relatively high rain rate amount can estimate. So these things is the dry air mass injections. It is enhance the rain rate. Such a situations and relatively occur in the moist environment. Such of things is improve the estimation of the rain rate by the Himari 8. This is our advantage, is this research. And next, I will be talking about the apply to the terrestrial monitorings over the land. So improve the frequencies observation of the land is also the opportunities cloud-free areas detections. So this is one of the good example papers, and he's also detected seasonality of the tree observed. So lower one, this is Suomi MPPs. This is and Leo observations, the seasonality of the NDVI. And this one shows the Himari 8 detected NDVIs, very improvement of the, and observations opportunities compared with the low elevation satellite. So easily to monitor seasonalities compared to low elevation satellite due to the frequencies improvement. Such of things can apply to the Amazon and tropical rainfall forest monitoring. Recently, NASA Ames groups published a paper in the Natures, and even though the tropical Amazon rainforest and significant and confidence rates seasonality of the forest phenologies can captured by the GOES-R and advanced baseline images. This is a good example. So they also I'm also my co-authors, and this is a high and NDVI and low NDVI's difference and months, and also here is the NDVI difference with the significant levels. Even though the tropical forest is due to the rainy seasons difference and seasonality in the NDVI also can capture. This says that maybe changing the paradigm shift, the monitors of and tropical forest monitorings by the geo. This can apply into the Himari 8 and maybe Indonesia's forest monitoring also improve, I think. It can apply to terrestrial monitorings. Okay, finally, I will be talking about the disasters monitors by the Himari 8. This case is a typhoon attacked in Japan. Unfortunately, 100 people died due to the typhoon attacking. Very big damage is occurs. Okay, this is we skip. So, and after the typhoon landings, and this is a flooded area also captured in the Himari 8. This is before the landings. This is after the landings. Here is the rivers. Around the river area is and natural colors image, and the color is also changing. This is due to 1.6 micrometers bands and utilizes this RGB compositions. 1.6 is very sensible to the waters. So this means that this is flooded area also captured in the Himari 8. So, okay, these things apply to the NDWI, normalized difference water index estimations for the Himari 8, just after the landings and typhoons. So this green color shaped area is the NDWI detects the flooded areas. This red and area is after that, and training data detected the and flooded areas, very and good relationship. These things I think and geostationary satellites, particularly third generation satellites, can more utilize the linkage between the geo and LEO, particularly for the request for the SAR. Just after the typhoon passed, where is the flooded? Firstly, geo checks. Then request will be done to the SAR or LEO. Then more prompt reaction will be done. So such of things I wrote the review papers here. Now is under the review. So okay, this is the final slide. And the closing remarks, messages are very simple. The third geo enhances the capacities for the monitoring the Earth environment, not only the weather, but also atmospheric, terrestrial. Today I'm not talking about that, but ocean environment. More utilization will be needed. An integrated link between the geostationary satellite and the LEO, particularly for the SAR, in the case of the prompt monitoring of the disaster event. But unfortunately, the geo data is very huge value. So how to handling is a crucial issue, I think, for more utilization. That's all. Thank you very much.
Okay, thank you. You're welcome, Miss Professor Higuchi Atsushi. What's a great presentation today. So
Thank you.
okay, so what I remark from your presentation is first maybe the more utilization will be needed in integrated link between generation geostationary satellites and LEO, like you said before, and particularly SAR in the case of prompt monitoring of a disaster event, and especially for Indonesia, that has the big potential in disaster because of the ring fire area. Okay, I think Professor, because the time is limited, so we will go to the question and answer section. Okay, for the first question came from there's no name, and the question is, what is the accuracy of geometric correction or positional accuracy for the Himawari H?
Yeah, and third generations generally improved the and navigation's information compared with the second generations. This will be, and this is the first step, and our output is also validated, and our geocollected product is also validated in the papers. In the Yamamoto et al. In 2020 in the Journal of Remote Sensing. And this indicates that generally the less than 1 kilometer's difference in the geocollections.
Yeah. Okay. Thank you, Professor. We'll go to the next question. The question is, there are different accuracy of geometric correction over the Indonesian land area, and what method do you use for automatic processing to improve geo accuracy?
Yeah, and this is and Indonesia is a very and located as a nadir of the geostationary satellite is and this and accuracy is and the best way compared with Japan. So and we this collection method is the phase of collection method we applied. This also description paper is written in the and also remote sensing. And please see that their papers.
Okay. Okay, Professor, I see.
Yeah.
Okay, and for the next is what method can be used for forest fire detection, Professor?
Yeah, mainly this is based on the thermal infrared and temperatures rapidly increases. Yeah, and also difference of the thermal infrared brightness temperatures difference in the thermal infrared. This is a kind of aerosol monitoring and detection because of such kind of and eruptions case is brightness temperature is 10 micrometers, 12 micrometers difference, and the 10 micrometer and 8 micrometers difference. Yeah, easy to monitor the atmospheric shapes difference particles. This is like in the forest fires.
Forest fire.
Yeah.
Okay, thank you, Professor.
Mhm.
And the next question came from Mr. Muhammad Arif Munandar. And the question is, Professor, Indonesia has many volcanoes and many convective clouds. And could Himawari 8 detect volcanic ash if there are convective cloud over the volcano? And if yes, how to detect it?
No.
Oh, no.
No, cannot detect.
Okay,
Due
okay.
to the optical sensor, cannot capture.
Okay, okay, Professor.
Mm.
I think we'll go to the next question. All we know, all we know is that SAS and SAR have a similarity. And please advise whether at Chiba University has a forum that discuss about SAS.
What means a SAS? I don't know.
Well, there is no mention it here.
Yeah.
No, yeah.
Hmm.
Maybe is it is there a forum that discusses about SAR maybe in Chiba University?
Uh-huh.
Maybe it's about satellite imagery radar maybe, Professor.
Yeah, I'm not sure about an SAS.
Oh yeah.
Sorry.
It's okay, Professor. Okay. Maybe we go to the next question. How many satellites can orbit together using geostationary method to monitor a same specific area, for example, in Japan at one time?
Yeah, many satellites. This was largely depend on each country's on the policies. For example, covers the whole of the Earth, whole of the globe in the 5 or 6 geostationary satellite is enough to cover. But and thinking about this is how to say this is and each country's policies, the observations by each own countries. For example, in the case Japan has the Himawari series geostationary satellite we have. Also, South Korea has a similar specification sensors geos also have only the 5 degrees difference. China also has a similar function satellite operator because basic information have to operate each own countries. This is largely, it sort of depends on each country's data policy and operations depend on. And that historically, the United States of America is a 2-orbit satellite operate covers the Pacific Ocean and the Atlantic. And the European people, European EUMETSAT also have the 2 satellite covers.
Okay, okay.
Yeah.
Professor, sorry, SAS means synthetic aperture sonar. SAS, what I mentioned before. Okay, the question I will return again. All we know is that synthetic aperture sonar and synthetic aperture radar have a similarity. And please advise whether at Chiba University has a forum that discusses about synthetic aperture sonar. Is there?
I'm not sure about these things.
Oh, okay.
Yeah.
Okay, and it's possible if synthetic aperture sonar and synthetic aperture radar interconnected, Professor.
Yeah, maybe in such kind of expert, I'm not sure about the Chiba universities. Maybe Yosafat and Professor Yosafat and some colleagues is expert is also available, but I'm not sure about the and SAS. Yeah.
Okay. I think there is no question again, Professor. So I say thank you very much, Professor Higuchi Atsushi, for your great presentation. We
Thank
hope,
you.
yeah, we hope your presentation increase our knowledge and insight. So such an honorable to meet you here, Professor.
Thank you.
Yeah, okay. Okay, I think before we end our tutorial, it's better for us to take picture together. Maybe host and co-host. Could you help me?
Okay, because there are 4 slides, I think we can start one by one. Okay, for the first slide, if you can turn on your camera, please turn on all the participant and the speaker. Okay, 3, 2, 1. And then the second slide, please turn on your camera. 3, 2, 1. The third slide, please. 3, 2, 1. And the last slide. Okay, it's done.
Okay, thank you, co-host, for helping me. So once again, I say thank you for Professor Higuchi Atsushi. Stay safe and stay healthy always. Okay. Okay, for all the participant, I would like to remind all of you, your certificate can be downloaded in the link in Zoom chat, and it will only be available on for today. About the time range is about from 5 p.m. In Indonesian time until 5 p.m. Okay, thank you. Okay, I think my time is up, so I will give back to the master of ceremony, Mr. Krishna. Thank you.
Okay, thank you so much. I want to say thank you so much once again to Professor Higuchi Atsushi. Arigato gozaimasu, Professor. And then I would like to, before you're going to end this third tutorial series, I would like to rememorize again to you, ladies and gentlemen, about the important date that the episode 2021 tutorial series, that the deadline for the abstract submission at the 13th April 2021, and then the deadline for the paper submission at the 31st May 2021, and then the notification of paper assistance at 1st August at 1st August 2021, the deadline for the final paper submission at 1st September, and then the conference for the first day until the last day from 1st November until the 5th November. And then I want to remind again to all of you, ladies and gentlemen, about the e-certificate links that has been sent by the host. You can take a look into the chat room because this because this form only open up into the 5 p.m. Western Indonesian time, waktu Indonesia Barat, and also only open up until 7 p.m. Japan's time. So maybe next I want to continue it to Dr. Wahyudi Hasbi, maybe to Bapak Dr. Wahyudi Hasbi as a representative of Professor Josafat. Maybe do you have any message, sir, to all of us here? To Dr. Wahyudi Hasbi? Maybe for some unavoidable J, maybe, yeah. So he couldn't give us about the ending, but it's okay. So maybe this is all about. Oh, please unmute. Okay.
You can, okay.
Please.
Okay, all right. So once again, thank you so much for all the distinguished speakers, Professor Higuchi, Atsushi, and also all the participants. And of course, a very great moment with the IEEE student branch of Institute of Technology of Surabaya. And also thanks again, my big thanks to moderator, Mbak Ulma, and also MC Mas Krishna for your help in this session. And as I mentioned again, see you soon in other tutorial. And of course, you still have time to submit your abstract in our conference, and see you soon in Bali after COVID, I believe. Okay, all right, bye-bye.
Oke, thank you so much from Bapak Dr. Wahyudi Hasbi. Terima kasih sekali Bapak. I want to remember us again about the next tutorial series, the fourth tutorial series episode 2021 that will be held at 22nd April 2021. That will be brought by the speakers Dr. Agustan, Dr. Adriano Meta, and Dr. Marwan Yunia. So maybe I would like to say that to all of you, ladies and gentlemen, to make sure that yourself get intended to the next tutorial series of the episode 2021. So maybe that's all about this day, about this third tutorial series episode 2021. I am here, Krishna, as your MC, and Toyifatul Ulma as moderator. Please excuse us here, and thanks for your attendance. And make sure to again, make sure to yourself to get intended into the next tutorial series, and see you again into the next tutorial series. Thank you, everybody. Thank you, everyone.
Terima kasih ya.
Terima kasih semuanya.
Terima kasih Pak Cahya. Pak Cahya masih ada enggak?